The next electrical device that I want to go over with you is called a Hall effect switch. It emits a digital signal. In the earlier Ford electronic injection systems, along with Chrysler and some other imports, European, the distributor signal was a Hall effect switch. With a Hall effect switch, we have a 12-volt supply, we have a reference ground, and we have a changing signal. The changing signal is a square wave that is grounded as it moves through the magnetic field of the Hall effect switch. And that's going to provide us a digital square wave pattern. So the profile ignition pickup, or the Hall effect switch on a Ford, is on pin 56 of the breakout box. I'm going to set up my time base here. I'm going to go ahead, because it's probably a 12-volt pulse, I'm going to move that voltage scale to 20. And time base, a half a second is a lot. We're going to really want to dial in closer to this. We want to get it to where we get at least 2 crankshaft revolutions. So we'll do 10 milliseconds per division. Now I'm going to have my assistant start the vehicle, and we'll capture the profile ignition pickup. Okay, I'm going to go ahead and stop or freeze that. We can go ahead and shut it off. So now you can see we have a digital square wave pattern. Voltage amplitude is right at 12 volts. The little notch on the right-hand side of the square is normal. That means that the computer is in control of spark timing. When you see that on a Ford thick film ignition, you know it's in control of timing. My question to you is, what is the skinny guy in the middle? We've got the wider square, wide square with the notch, like someone took a bite out of the sandwich at the top corner. And then we got the skinny guy that there's no bite out of the sandwich. What is that? Well, this 5-liter Ford 95 engine is what's known as sequential fuel injection. Each injector has its very own channel, and the injectors are fired in a sequence. The computer has to know where to start the sequence. This vehicle has a distributor. So what we do is we modify one of the square blades as an indication of number 1 top dead center and when to start the sequence of firing the injectors. If we didn't have a distributor, we'd still probably use a Hall effect switch, but it would be called a camshaft sensor. So this narrow skinny guy in here, that's our cam sensor. And it's all built into one Hall effect that we can basically look at profile ignition pickup and our trigger or our cam sensor. When you're looking at a square wave pattern, you want to look and make sure there's no noise at the bottom of the square that could indicate that you have a ground problem. You want a nice, clean, crisp square wave. Of course, the bite out of the sandwich on this particular Ford is normal, but you're looking for a clean square wave pattern. The computer is going to utilize this information. This is how it knows RPM. This is how it knows how to synchronize the injector firing. So this is a very important sensor. Without this sensor, you're walking. You've got to have a crank signal or a distributor reference pulse, as some manufacturers call it. Ford calls this the profile ignition pickup. This is the input into the computer. Now the computer has this information. The computer is going to want to control timing. So it's going to send a signal back out to the distributor called spark output. When the computer talks, computers are digital. So let's take a look at the spark output signal, the signal coming from the computer back to the distributor, which is telling the computer what it wants to do as far as firing the coil and controlling spark timing. So I'm going to go ahead and release my freeze. Our time base that we've got set up and our voltage base should be pretty good for the spout signal. So let's go to pin, let me look at my cheat sheet here. Okay. So now we went to pin 36, which is the spark output signal from the computer to the distributor. The trailing edge of this square wave pattern is going to be where the computer, once the ignition coil to fire or control spark timing. Notice that the bite out of our sandwich, as to say, is on the left-hand side. You need to know that is normal when you're on the spark output. This is the same signal back at the breakout box, pin 36, that you would unplug as far as a spout connector to set the base timing on the distributor. So your input is the PIP, Profile Ignition Pickup Hall Effect, and the output is a digital signal from the microprocessor, the computer, so it can control spark timing. So we could, being it's a multi-channel scope, we could look at PIP and spout, and if we looked at the differential, as it changed, you'd be looking at spark timing. The difference between the trailing edge of the square on a PIP and the trailing edge of a spout would indicate the amount of timing degrees in crankshaft rotation. The next electrical device we're going to look at is called a temperature resistive or hot wire mass airflow sensor. The mass airflow sensor is God in most volumetric fuel injection systems. It tells the computer how much air is coming into the engine. In return, the computer will know how much fuel to deliver and maintain as close as possible, when not in power enrichment, a stoichiometric air-fuel or perfect air-fuel ratio. So the mass airflow sensor is on pin 50. So we want to turn the key on. I'll check my parameter settings. Basically, the mass airflow sensor is going to low airflow around idle, or probably be around a volt. And as we accelerate or take a gulp of air, the voltage is going to go high and it's probably going to exceed 4 volts. So the voltage is the transfer function. That transfer function will be transferred, say a volt might be 9 grams of air per second at idle. 4 volts might be 300 grams per second. That transfer function is built into the programming of the computer. But we want to look at the raw data. So in my parameter settings, I'm at 5 volts, a DC signal, and I'm going to go ahead and bring this away. And let's go ahead and start the engine. One of the nice new features of the Alltel is a low-pass filter that I can turn on to take away some of that hash. So I'm going to turn it on, clean it up a little bit. And we're just going to snap the throttle, and I'm going to take a picture of the mass airflow sensor signal. So go ahead and have my assistant snap the throttle. You can shut it off. The 5-liter engine sounds pretty healthy. So you can see here, we were running under about a volt, and as you snap the throttle, airflow increased into the engine. You can see the initial gulp of air, and in a traditional mass airflow sensor signal pattern, it looks like this. There'll be a straight line up, and then there'll be a dip in there as it's reaching its volumetric efficiency of breathing when we snap the throttle. We want to make sure we snap the throttle, that we go over 4 volts. That's a good tip. The mass airflow sensor pegs at 4.79. The computer doesn't know any number above 4.79. It may know that 4.79 is 300 grams of air per second, but at 4.80, it doesn't know whether to add fuel or subtract it. In some performance applications, a guy will improve the breathing capabilities of the engine with cylinder heads and camshaft that he exceeds that flow, and you'll have to use a larger mass airflow sensor. If the mass airflow sensor temperature resistive wires are dirty, they're insulating it from the true airflow into the engine, and you won't get this type of voltage or this type of pattern. So we can analyze very quickly with the lab scope the mass airflow sensor. This happens to be a 1995 Ford 5-liter EFI, but in our industry, the mass airflow sensor signal output will either be 0 to 5 volts, or it'll be a digital output in a frequency. General Motors likes to use frequency mass airflow sensors. As the airflow increases, the frequency increases. So we would see a digital pattern, or the squares per second increasing with airflow. With an analog voltage like this Ford, many European, Asian imports, we just have a linear signal that increases with mass airflow. The mass airflow sensor is more accurate than the early days of a vane airflow, because if moisture tries to cool that wire, on this Ford one, the hot wire is going to be maintained at 200 degrees Celsius. As air comes in, it tries to cool the wire. A proportion of the voltage that's utilized to maintain the wire at a constant temperature is revealed to the computer, and the computer interprets that data as an increase of airflow. So voltage goes up, airflow goes up. This mass airflow sensor looks excellent. I know some shops don't clean mass airflow sensors. Some of them replace them, and I understand why. But in this case, this mass airflow sensor looks absolutely good. So let's move on to another sensor.